Good morning. So today I'll be presenting on critical mineral assessments with AI support, or critical mass. This was a collaboration between the USGS, the Defense Advanced Research Projects Agency, and the Advanced Research Projects Agency Energy. The program ran from August 2023 to February this year. It produced new AI ML tools for conducting mineral assessments, and we are now in the stage of transitioning these tools from research to operations. So mineral resource assessments have been a core function of the USGS since its inception, and the techniques developed in the 70s and 80s really haven't changed that much over the years. Essentially, assessments try to answer three basic questions. Where do mineral resources occur? What is the nature of their occurrence? And how much resources do we have? So we synthesize available information on mineral deposits, what commodities may be present, and make predictions of undiscovered resources to identify opportunities for economically and environmentally viable resource development. Assessments require expertise in GIS, statistics, geology, geophysics, geochemistry, and remote sensing. For any assessments, we require, at a minimum, mineral occurrence datasets and geologic maps. These are examined in conjunction with exploration history and mineral deposit models to make estimates of the number of deposits and the value of resources in an area. Additional datasets that may contribute to an assessment include geophysics, geochemistry, and remote sensing data. The data we have available to us are of various vintages, scales, and quality. Thanks to EarthMRI and other projects, we have a lot of great new geophysical datasets and reanalyzed geochemistry samples, as well as new 24K geologic maps. But these data have limited coverage. We also have a lot of legacy data sets. They contain a wealth of information, but not all the data are digital or ready to use. And for remote sensing data, like hyperspectral and LiDAR, we have not yet fully realized their potential for applications in our mineral resource assessments. As part of a scoping effort we did with DARPA in 2022, we put together this diagram of the mineral resource assessment workflow. Most of our time is spent compiling and processing data that are found in historical documents and digital databases. The process is highly manual, requiring trained geoscientists to identify relevant reports and data sets and extract necessary information. And we now have more information than at our fingertips than we can reasonably make sense of. So this is where we could really use newer methods and technologies. And we don't just mean generative AI and machine learning, but also statistical methods, modern data formats, custom software, and cloud computing. So the Energy Act of 2020 gave us a clear mandate to assess all domestic critical minerals, but didn't provide any additional funding to do so. The bipartisan infrastructure law, fortunately, did commit some funds and extended the timeline a bit, but for many critical minerals, we may never have conducted an assessment. We may not have all the data that we need, and knowledge gaps may exist that require a lot of basic research. And this takes time. It typically takes about 2 years to do an assessment for a single deposit type for a commodity. So for 50 critical commodities, that's 100 years. So clearly, we need to find ways to accelerate that timeline, and we need to be creative in how we can do more with the existing funds and staff. So this is where the collaboration with DARPA came in. So DARPA was very interested in our dependence on critical minerals for their use for defense applications. And with their support and funds from ARPA-E and USGS, we were able to get a new program off the ground to try to accelerate critical mineral assessments. The new program, titled Critical Mineral Assessments with AI Support, aimed to automate and accelerate key time-consuming processes and make results reproducible and limit duplication of effort. The program was designed around the geoscientists with the intent of reducing time on tedious tasks so scientists could have more time for investigation. The program structure for critical mass was modular with 4 technical areas, or TAs. TA1 focused on maps, TA2 on mineral feature engineering from documents and data sets, TA3 on mineral prospectivity mapping, and TA4 on human-in-the-loop learning. Sitting at the center of the program was the cloud-hosted Critical Mass Data Repository, or CDR. The CDR is essentially a warehouse of public domain data that outputs from TA1, 2, and 3 models. The CDR allows assessment scientists to all have access to the same data, helping us address problems we have historically encountered related to downloading, editing, and maintaining copies of datasets on separate machines. The program was organized around a series of hackathons with the kickoff in August 2023 at the National Conservation Training Center in Shepherdstown, West Virginia, and the final evaluation demonstration event in January 2025 in Reston, Virginia. So we had over 50 computer scientists and software engineers from universities, research institutions, and small businesses participated. And almost as many USGS scientists participated over the course of the project. 18 months was not it wasn't a whole lot of time. So the in-person interactions were invaluable to making a lot of progress very quickly. So every 3 months, performers would essentially sprint on a new challenge. The first TA was focused on processing geologic maps. We have a great mapping program at the USGS, including a database of over 100,000 maps of various ages and scales. Many of these maps have not been digitized, and we only have them as scanned images. It's a tremendous amount of work to vectorize map features, as well as extract all the rich textual information contained in the geologic map using traditional GIS tools. So from the beginning of our discussions with DARPA, we emphasized the need for tools to reduce the amount of time it takes to digitize these maps, recognizing that there will always be the need for some human input. If we can get 80 or 90% of the way there, that would be a huge time savings. This is an overview of the different components of the TA1 workflow. We start with segmenting the map image, identifying which part of the map is the map frame and which part is the legend. We segment the legend and store that information in a JSON file. Then we georeference the maps, typically starting with the corner coordinates. Using the legend, we extract the different features from the maps. And then we combine all the extracted features with basic attributes and save them to an open source format like GeoPackage or GeoJSON. And here's an illustration of the steps I just described. So when a map is submitted for processing, machine learning and computer vision models will segment the map into its component parts, OCR the document, and detect legend items, georeference the map, and extract point, line, and polygon features. The second technical area focused on mineral sites, trying to make sense of unstructured data, tables, and figures buried in PDF documents. For assessments, we need the best available location and attribute information, and often that information is not all in one place. So it requires a lot of search, compilation, and cleanup. TA2 attempts to address this need through the construction of a knowledge graph from mineral occurrence data sets and technical reports on mineral exploration, along with tools to extract grade and tonnage information and classify deposits. For those of you unfamiliar with the term, a knowledge graph is a structured representation of knowledge that captures relationships and entities, enabling improved information retrieval. Here's a preview of MinMod. This is a browser interface that allows users to interact with data in the knowledge graph with tabular and map views and capabilities to query, filter, edit, and export data. We built a huge compilation of mineral site data, all accessible in one place. So there's still a lot of cleanup to do on this, but it can all be done in one place with version tracking, which is a huge improvement over what we've done in the past, working individually on subsets of the data and never syncing edits back to a central repository. The CDR takes the outputs from TA1, TA2, and stores them in a way that TA3 can access them. So we have geologic map data, mineral site data, as well as directly uploaded geochemistry and geophysical data layers. TA3 is centered on assembling these input data layers, pre-processing them, and building machine learning models to make predictions about where undiscovered mineral resources are likely to occur. The outputs of TA3 include raster layers showing the probability and associated uncertainty of a mineral deposit occurring at a particular location. The maps essentially tell you where to look for undiscovered resources and perhaps where to focus additional data acquisition efforts. This is an illustration of what that looks like. So we can iterate on this process as many times as we like, refining our evidence layers, testing different models and different parameters, having domain experts review results, and incorporating their feedback into new models. Over the course of the program, we ran a dozen or so different models for different deposit types and areas, with engagement from USGS folks with different backgrounds. And the results look pretty reasonable. The TA3 models can help reduce data dimensionality and improve explainability by providing us with the ability to look at the influence of each input on the prediction across the map area. And finally, through TA4, user interfaces were developed to run the tools and explore and edit input and output data sets without the need to code. Here's a quick glimpse of some of the HMIs that were developed. This is the Polymer Maps app for running TA1 tools. You can search maps or upload a new map, submit a job for processing, and view outputs of TA1 tools. And you can, there are also tools to edit those outputs and download them if needed. These are images of the Polymer Docs app for ingesting new reports for TA2 pipelines and selecting map images from documents to submit to TA1 tools. We can access reports in the USGS publications warehouse, as well as a large collection of mining reports. And we can also upload new reports. And finally, StatMagic, through which users can run prospectivity models. This interface allows users to query the CDR to pull together evidence layers and training sites, build a model, run it, and view and download results. So just a list here of some of the accomplishments of the critical mass program. So over 18 months, we developed over 20 different tools. We built a central data repository that integrates inputs and outputs from all tools. The modular engineering framework, combined with cross-TA collaboration, led to the successful integration of the tools. The HMIs do not require coding. The USGS provided data and feedback that were critical to the success of this program. And there's great potential to save time and reduce duplication of effort in assessments using these tools. So the current status, essentially we are attempting to transition the tools and test them in our system. And we're beginning to integrate them into active assessments. We have reports, journal articles, and presentations in progress, and we're continuing to work with stakeholders. So very quickly, I'd just like to share a preview of some critical mineral assessments currently in the works. These include crystalline graphite and lithium-bearing deposit types and magmatic nickel PGE, commodities that are vital for battery and energy storage systems in portable electronics and EVs. Here's an example of a neural network-based predictive map of orogenic graphite potential in the Appalachian Mountains. It was developed using the critical mass TA3 models. We're using newly acquired Earth MRI geophysical data to inform assessments. These figures show how airborne electromagnetic data have helped us refine permissive areas for graphite. So they're shown in black on the left, and it's a little hard to see, but yeah, the yellow and blue and green areas on the right are permissive areas. And we have 2 papers in review now on lithium pegmatites related to the Appalachian origin. One in the south where there are known deposits, and one in the north where significant mineralization has been reported in Maine. And finally, an image of a national scale prospectivity map for magmatic nickel that was developed using critical mass tools. Red areas indicate high prospectivity, and the shades of gray indicate uncertainty. And the points on the map are mineral sites that were used for training, validation, and testing the model. And with that, I'd just like to thank our partners and open up for questions.